So we're going to go through exercise 1, the use of the microscope. Um, in micro, using a microscope is a critical part of what we do. The size of our specimens is so small that we need extra equipment to be able to see them. The extra equipment is a microscope. So there are three primary types of microscopes in use today: a dissection scope, a compound scope, and an electron microscope. So, dissection, compound, and an electron microscope. So let's talk about the dissection scope first. Dissection scopes usually magnify up to 50 times what your naked eye can see. Okay, so we're not talking about something that we couldn't see at all with our naked eye. Usually they are binocular, meaning that you've got two places to look. And that actually allows us to see in 3 dimensions because it gives us 2 points of view, one with each eye. Usually it is used to magnify objects that can be seen with the naked eye. So, for example, if I'm a coin collector, I want to look at the surface of a coin that I am buying to see what damage is there, whether something is intact, but maybe I can't see that with my naked eye. Instead, I use the dissecting scope to kind of magnify the surface of what I'm looking at, to see if there are scratches in any specific places, if there are dents in any specific places. The place that you see these used the most as far as everyday individuals would be jewelers and coin collectors. Again, jewelers can use it to look at the surface of a jewel that they've got. Is it scratched? Is it intact? Does it have whatever number of facets that I need? If it's a small gem, you're not going to be able to see that with the naked eye, but you can with the dissection scope. As far as biology goes, we usually use it to look at surface anatomy. So let's say a dragonfly wing. Technically, I can see a dragonfly wing, but let's say I want to know the details of a dragonfly wing. I would use a dissecting scope to help to magnify and give me a 3 dimensional image of what I'm looking at. Now, the compound scope. This is what we use, okay? It actually does use a system of lenses, usually two, to help to magnify what we're looking at on the stage itself. Okay, so this is the stage. This is where we put our slide. What that does is it basically magnifies something up to about 1,000 times what our naked eye can see. So our naked eye would be 1. That would be what our eyes see. It can go up to 1,000 times what our eye can see. That X just means times. It says unit. Okay. In order to provide a better image, though, light actually has to pass through whatever you're looking at. If you've got something that is very, very thick, the light won't pass through it. You won't be able to use this type of microscope. The light has to come through it almost like a transparency, or let's say a film strip, where the light has to go through so that you can see the image. If you made it completely black, no light would pass through it. You wouldn't see anything. For us, what that means is whatever we're looking at has to be very, very thin on the slide so that the light can come through, very small. Okay. Most of the time, when you've got a specimen that has been sliced like that, um, or for that matter, bacteria, which is what we would use, the light coming through it will not allow you to see detail because it is so thin. There's not going to be a shadow. There's going to be nothing there for you to actually contrast enough with so that you can see it. So what do? We dye our specimens. We actually put them in Technicolor so that there's contrast so that we can see it as the light shines through it. If you don't do that, you won't see anything, especially with bacteria. With the bacteria, they are so teeny tiny, you're never going to see anything. Okay, so most of our specimens using this type of microscope, the compound microscope, is or are between 25 nanometers and 1 millimeter in size. And we're talking bacteria in this case. Now, the last type of microscope I'm going to mention is the electron microscope. It was developed in the 1940s. For us, this was life-changing. This was a huge breakthrough for the scientific community because it allows us to magnify things that we were never able to magnify before, or at least the number of times we're able to magnify. So how does it work? Well, you have your specimen, you put it on a specimen stage, basically. You put it into the machine and it creates a vacuum. That limits what we're able to do. If you want to look at something alive, you're never going to look at it alive inside of a vacuum. So whatever we look at with an electron microscope, it's going to be dead. So you put it in a vacuum and you bombard it, basically you shoot electrons at it. And as those electrons bounce off, it creates a three-dimensional picture based on the, how do I put it? Based on the shape that is created as those electrons bounce off. So it's kind of a derived picture, but it's a picture. So again, drawback, nothing can be alive. The benefit, this allows us to see things magnified 10 to 200,000 times what our naked eye can see. The compound scope didn't do that for us. Remember, it's 100. So the fact that we've got something that can do it that much allows us to see a lot of things that we weren't able to see before. Now, coming into the present age, even before the 1940s when they invented this, we now have the ability to take digital photographs. With the digitization, I'm just going to go with that word, of photographs, that also means that we can zoom in on those photographs. That actually allows us to see 2 million times bigger than or smaller than what our naked eye can see. We can actually take advantage of the fact that it's a digital photo that we can zoom into to see even more detail, greater detail. This machine actually allows us to see all viruses and most molecules. So not necessarily individual atoms, but we might be able to see a sugar crystal or caffeine or chocolate. Okay, so it allows us to actually see the molecules themselves. All right. So looking at the microscope, here's our microscope. You have the two parts of the scope that you look into, okay, to see your specimen. These are called the oculars or the eyepieces. And for us, we have the binocular. We've got two of them. Like I said with the dissecting scope, that gives us depth. We can actually see depth with that. Coming down from there, you have the arm. The arm is actually what holds this portion of your scope above this, which is called the stage. Now, in a play, the stage is where the actors are. It's what you're looking at, right? Same thing here. So the stage, hang on one second, is where your slide is so that you can look at it. Okay? So this arm is actually kind of connecting the bottom to the stage to the top where your oculars are. Coming down this direction, you've got this right here. See how it revolves? This is called the revolving nose piece. Attached to the revolving nose piece are these things right here. You may not be able to see them with my black t-shirt. These are called objectives. And each one of these objectives is a different magnification. So the first one, the shortest one, the shortest one, is actually 4x. So it increases magnification 4 times what my naked eye can see. The next one is 10x, 10 times what my naked eye can see. The next one is 40, so 40x. And then the last one, which is a very special one that you only use under specific conditions, is the 100x. Okay, so you have oculars, the revolving nose piece, the objectives, the stage. Now, the stage itself actually has clips, see this, to hold your slide in place. So when I put my slide on here, I let go of the clip and it holds it in place so that my slide can't slip and slide all over the place. I don't want that to happen, okay? So I've got this stage, the stage clip. One of the things that I mentioned before was that light coming through the specimen has to be very controlled, right? I have to be able to not make it so bright that things bleach out, which can happen. So what do I do? Well, I've got two things that help me to control the light coming through my specimen. One of them is actually within the base of the stage. See that piece of glass right there? You can also see it here. This is called the condenser. So light just kind of goes out in every direction, but if I want it to hit my slide at a specific point, I kind of have to guide it and put it where I want it. The condenser takes all of those light beams and condenses them down into one beam so that it goes through my specimen exactly how I want it to. Now you can move the condenser, kind of have it spread out a little or come together. There's a knob under here that will allow you to move it further down from the stage or move it closer to the stage. But the condenser, its job is to condense the light, just like the name implies. Also, underneath the stage, you have the diaphragm, which I'm sure some of you have learned the iris diaphragm. Okay. This actually allows you to make the hole that the light is going through smaller or bigger. So if I turn this toward you, see that little pinpoint of light? Right now, my iris is closed. Where did the little knobby go? There it is. Now watch it. Watch this. See how it got bigger? It's smaller. Just like the iris of your eye, controlling how much light goes into your eye, this iris diaphragm is going to control how much light is actually going through your specimen. With micro, you have to remember that a lot of light can completely bleach out what you're looking at, especially as you get into greater magnification. Sometimes that means that you have to kind of dim the light a little so that you're not basically bleaching what you're looking at, photo bleaching. One second. All right. So we've got the condenser, we've got the diaphragm, the stage clips, the objective lenses, the nose piece, the eyepiece, the arm. Sorry. As we travel down, you'll notice these two knobs. I've got one here on the outside, and then I have this one here on the inside. The inside one kind of pooches out a little. The outside one is right up against here. And you'll notice that the one right next to the body of the scope moves the stage, if you look at the stage, a lot. Whereas the one on the outside here, if you look at the stage, doesn't really move it all that much. It's moving it, but it's not moving it by leaps and bounds like this knob would. So the one that moves it a lot with very little effort is called the coarse adjustment. It's coarse, it's not fine, it's basically just moving it up and down in huge distances. My fine adjustment, however, while moving the stage, doesn't do it that fast. I mean, I can sit here and I can do this, and you would still really not see this moving by a lot. The fine adjustment actually helps to keep your ability to focus kind of limited. So when you look at a specimen, I'm going to put my specimen back on my microscope. When you look at a specimen, and because my eyes are so close together, I'm going to turn this around so I can see it better. The first time that you are using it, okay, and you want to focus in on your slide, you will use the coarse adjustment and your lowest magnification, so minus 4x. Now, when I use that coarse adjustment, I should be able to get it into focus relatively quickly. And because it's only 4 times more what my eye can see, it's not necessarily that hard to get it into focus using this and the coarse adjustment. Now, if I want to increase my magnification, so if you look at the distance here between the bottom of my objective and the top of my slide, there isn't a lot of room. But when I increase the magnification, look at how close that now is to the top of the slide. If I were to use the coarse adjustment and move the stage a lot, there's a real good chance that my objective would jam into my slide, break the slide, possibly break the objective. So what do? Instead of using the coarse adjustment in here, I'm going to use the fine adjustment knob here, okay? So that helps me to focus without moving so much. Now, I'm going to go up again to 40x. See the distance? Watch. That is like right on top of my slide. So I can't use that coarse adjustment because if I move it even 2 millimeters, I'm going to ram through the slide. So what do? I use my fine adjustment knob again. And that allows me to move the stage to focus without necessarily moving the stage to focus. So I've got my fine focus and my coarse focus, or my coarse adjustment knob and my fine adjustment knob. Okay? So I've got those two. At the bottom here, I've got two pieces. I've got the base, that basically is the base of the scope, and I've got a light source. So with this scope, here's the base, here's the light source. And for modern times, this is an LED light. We charge the scope up, we unplug it, and we're able to use it pretty much the entire semester. So you can adjust the amount of light because we have a dial here that will allow us to do that. But the light source is what is actually creating the light that goes through our specimen so we can see our specimen. All right. So magnification and resolution. They are two different things, but they are two things that we need. Magnification is how big the thing is that we're looking at, how much we enlarge it. Okay, and I'm sure everybody has done this where you see a picture on the internet and you want to enlarge it. So you start making it bigger and bigger. And as you make it bigger, the picture becomes more and more unclear. That's a loss of resolution. You don't have good resolution with that. With a microscope in microbiology, you can't just have magnification, because if it's just magnification without resolution, you lose all the details of what you're looking at. So here, these three pictures are all the same magnification. What's the difference? The resolution. That has no resolution. Did we magnify it? Yeah. That has a bit more resolution, but it isn't all that great. This has both magnification, we can see the details, so it has resolution as well. The resolution, or the resolving power, is the ability to distinguish between 2 points in space. Here, I don't even know that I have two bubbles that I am looking at because the amount of detail here, the amount of resolution here is so poor. Being able to see small details, that's resolution. When it comes to a microscope, we want both. We want the ability to make the image enlarged, and we also want the ability to see the details. Having resolution but no magnification doesn't work. Having magnification but no resolution also doesn't work. So there's balance.